Look at your hand. If you zoom in past the skin cells and proteins, you eventually hit a microscopic void populated by trillions of atoms. For most of human history, observing this microscopic world was a physical impossibility. Lacking microscopes to see these building blocks, early scientists mapped this world through pure deduction. In 1803, John Dalton proposed his atomic theory. Atoms were tiny, indivisible, solid spheres that behaved with the heavy, rigid physics of billiard balls. Dalton's model successfully explained basic chemical reactions, leading scientists to accept it as an absolute truth for nearly a century. Science relies on the most effective model available to explain reality, at least until new physical evidence breaks that model apart. In 1897, Thomson discovered the electron. He proved the existence of a tiny particle with a negative electrical charge. This discovery created a crisis. If an atom contains smaller, negative parts, Dalton's indivisible solid sphere model was no longer viable. In 1904, Thomson proposed the Plum pudding model. He theorized a diffuse ball of positive charge that neutralized the negative electrons embedded within it, like blueberries in a muffin. The atom was no longer a solid block of matter. It was a complex internal environment, triggering a global race to map its geography. In 1909, Ernest Rutherford's team set out to physically test Thomson's model by firing heavy, positively charged alpha particles at a sheet of gold foil so thin it was only a few atoms thick. Look at the expected result. Heavy alpha particles should punch straight through the positive pudding of gold atoms without resistance. But the reality was shocking. While most passed through, some deflected at sharp angles, and a fraction bounced straight back. Rutherford compared this to firing a heavy naval artillery shell at a piece of tissue paper, only to have it bounce back and hit you. This led to Rutherford's nuclear model. He concluded that the atom is almost entirely empty space, with its mass and positive charge concentrated in a microscopic, dense center called the nucleus. A single, undeniable physical anomaly erased the accepted model overnight, shrinking the core of matter to a fraction of its previous size. There was a massive flaw in the nuclear model. According to the laws of classical physics, this structure was impossible. Negatively charged electrons orbiting a positive nucleus should constantly lose energy. They should spiral inward, causing the atom to collapse in a flash of light. In 1913, Niels Bohr attempted to solve why all matter in the universe doesn't spontaneously implode. Bohr adapted the model using quantum theory. He suggested electrons are locked into specific fixed distances or energy shells, jumping between them rather than spiraling. When physical models defied the known laws of physics, theoretical mathematics evolved to bridge the gap and stabilize our understanding of matter. By the 1920s, Rutherford had subdivided the nucleus into individual positive particles called protons, but the math still didn't add up. This is the missing mass anomaly. As this scale shows, the total mass of an atom was significantly heavier than the sum of its known protons and electrons. In 1932, James Chadwick identified that hidden mass. He discovered the neutron, a third particle inside the nucleus with a proton's mass but zero charge. The discovery of the neutron balanced the mathematical scales, providing the final piece of the atom's structure and making the nuclear age a physical possibility. Here is the modern atomic model, a dense core of protons and neutrons enveloped by clouds of electrons in specific energy shells. We arrived at the structure not through a single vision, but through a century-long relay race of brilliant and often destructive experiments. These physicists shared a defining trait, a total willingness to discard their own foundational assumptions the moment the physical evidence demanded it. The evolution of the atomic model stands as a testament to the scientific method's power to refine our understanding of reality through rigorous physical evidence.